Hello and welcome to 12.8, the Counting Principle and Permutations. Okay, the counting principle. If a first experiment can be performed in m distinct ways and a second experiment can be performed in n distinct ways, and the two experiments in that specific order can be performed in n times n distinct ways. And we saw this earlier. Was it 12.5, I think? A standard Nevada license plate has 6 characters, 3 numbers, followed by 3 letters. Repeats are allowed. In this scheme, how many license plates are possible? So, 3 numbers followed by 3 letters. So, 3 numbers. You could have 10 numbers, 10 numbers, 10 numbers. 26 letters times 26 letters times 26 letters. So this will allow Nevada to have 17,576,000 different license plates. Okay, next one. Sarah, Angela, Corey, Mercedes, and Heather are in a race. How many different combinations are there for the order of the finishing of the race? First, second, third, fourth, and fifth. So the thing to think about there is how many people could come in first place? Only one person, but there are 5 possibilities. There are 5 different people who, any one of whom could be first place. So that's 5 for first. Now, the first place is taken. First person crosses the finish line. How many people are left for second place? There are 4 left. Okay, the first 2 slots are gone. You still have 3 people in the race. Any one of the 3 could win third place. 2 people left. Any of the 2 can get 4th place, and only one person can get the 5th place then. If you multiply that out, you end up with 120 different arrangements. So this brings us to the concept of a permutation. The permutation is any ordered arrangement of a given set of objects. Now, in a permutation, order is important. The first one selected is important. What comes first, what comes second. That's an important thing about permutations. So number of permutations of n distinct items is n factorial, symbolized by n with an exclamation mark. N factorial is n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1. So most of your calculators will have the factorial button on it. One of the ones I use for my classroom, it's a TI-30, and the factorial is within a menu. The ones like this one here even, this is the TI-89. And this one's in the menu too. It's under the math and the probability menu. So a lot of them have it on there. Some are actually on the keyboard and you hit like a second or a third button for it. In how many different ways can Keith, Sarah, Jennifer, Jinky, Michelle, and Denver be arranged in a line? Well, this is 6 factorial. 6 people. 1, 2, 3, 4, 5, 6. And 6 factorial, put that in the calculator, that's just 720. That's 6 times 5 times 3 times 4. Sorry, 6 times 5 times 4 times 3 times 2 times 1. I can't count. Okay, example 4. Simone, Heidi, Stephanie, Jody, and Kyle are competing to have the top 3 scores in the class. So we have 1, 2, 3, 4, 5 people competing for the top 3 scores. So we have 3 spots. How many people are in the running for the first spot? There are all 5. How many people in line for the second spot? Well, once one's gone, there are 4 left. And then for the third spot, there are 3 left. 5 times 4 times 3 is 60. Okay. We go on to the next page. So a permutation formula, this is a little different than what we just saw. What we saw earlier was if you had all n things, then it's n factorial. But the number of permutations possible, number of arrangements possible when R objects are selected from n objects. R is less than n. Like in the last problem, we had 3 out of 5. That's going to be NPR, not National Public Radio, which is n factorial over n minus r factorial. Now most of your calculators have this button as well in the probability menu. The board of pharmaceutical company has 9 members. One board member will be selected as vice president of marketing. A different board member will be selected as vice president of research. How many different arrangements of the 2 vice presidents are possible? Well, there are 9 people on the board, and there are 2 positions. So we're looking at 9p2. That would be 9 factorial over 9 minus 2 factorial, 9 factorial over 7 factorial, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, over 7 times 6 times 5 times 4 times 3 times 2 times 1. So the 7's go, 6's, 5's, 4's, 3's, 2's, and the 1's don't really matter. And we're left with 72. Now a shortcut to that, we could have said 9 times 8 times 7 factorial over 7 factorial and just divided that part out and then had our 72 as well. Or you can use your calculator to get these. Okay, again, pause if you like. I'm going to move on. A disc jockey has 9 songs to play. 5 are slow songs and 4 are fast songs. Each song is to be played only once, and how many ways can the disc jockey play the 9 songs if the songs can be played in any order? In any order, that'd just be a 9 factorial. And by our calculators, that's 362,880. But what if the first song had to be a slow song and the last song had to be a slow song? So we know that we have a first song, a bunch of other songs, and then another song. Slow here, slow here. So we'd have 5 to choose from that, 4 to choose from that. And then the rest, 2 of our songs are gone, so we have 7 left. 7 factorial. And that would give us 100,800 different arrangements. What do the first 2 songs have to be fast songs? Well, we have 4 fast songs. So the first one's fast, and the second one's fast. Then the rest of them are slow, or whatever. And we end up with 60,480. Go on to the last page here. Permutations of duplicate objects. The number of distinct permutations of n objects where n1 of the objects are identical, n2 of the objects are identical, and nr of the objects are identical is found by n factorial over n1 factorial times n2 factorial times nr factorial. So determine the number of permutations of the letters of the word selection. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So in the word selection there's one S. I should do this. S there's 1. E there's 2. L there's 1. C there's 1. T there's 1. I there's 1. O there's 1. And N there's 1. So we'll have 9 factorial over 1 factorial times 2 factorial times 1 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 factorial. And that will give us 181,440 different arrangements of the letters in the word selection. And again, this part came out because there are 2 E's. Okay, well that's it for section 12.8, permutations. I will talk to you guys later. Send me your questions.